Welcome to Topcast and to question number 10 in my series of questions for David. And today it's one about dark energy, which is a topic dear to my heart because, as many will know, I spent most of my formal training, so to speak, in studying astronomy. And dark energy is one of those big open questions, maybe the biggest that we know of at the moment. I'm old enough to remember sitting in astronomy lectures at the University of New South Wales, learning about the Big Bang, learning about cosmology, learning about the mathematical ways in which we could predict what's going to happen next as the universe evolves. And what I remember learning is about the Big Bang, of course, and then about how after the Big Bang, because the universe cooled, we should expect the expansion of the universe to slow. And if the expansion of the universe slows, there are one of three things could have held. One is that the universe just continues to expand off forever, but just asymptotically getting slower and slower and slower, getting ever closer to becoming zero expansion. So it sort of just expands forever at an ever decreasing rate. That was one possibility I was told about. Another possibility was, well, the universe could be very finely balanced, finely tuned, such that it would expand just so far and stop, and then it would stop at that particular size. That seemed a bit unusual. I don't think anyone really thought that could be a possibility. The most common possibility among astronomers, at least as far as I'm aware of, at that time, this was 96, 97, something like that, were the astronomers who were saying, well, we expect a big crunch. We expect a reversal of the expansion. The universe will expand and then get to so big and then fall back in on itself, much like the explanation for why, if you throw a ball up in the air, it comes back down again, because eventually gravity wins over the thrust of your hand, unless you have a source of energy on that ball like a rocket propelling it upwards. So that's what we thought. We thought that it had to be one of these things. Whatever the case was, the expansion of the universe had to slow down. Whether it reversed or not was an open question. So it was such a huge surprise, to put it mildly, in 1998, when two teams of astronomers, one of which was Saul Perlmutter and one of which was led by Brian Schmidt, we claim him as an Aussie, found that the expansion of the universe wasn't slowing down and it wasn't going to stop. But instead, it is accelerating its rate of expansion, which is a phenomenal discovery. And what they did, of course, these two teams, independently of one another, was they looked at the luminosity, the brightness, of Type 1a supernova. Type 1a supernova are where you have a white dwarf star accreting material. A white dwarf star has an upper limit on its mass of 1.38 times the mass of the Sun. This is called the Chandrasekhar limit. The reason that it has an upper limit of 1.38 times the mass of the Sun is because any bigger than that, and the gravitational force is so great as to overcome what's known as the electron degeneracy pressure, so the repulsion of electrons against electrons in the atoms that make up the white dwarf star, that is overcome, that force of repulsion is overcome by gravity, causing the entire white dwarf star to collapse in on itself into I guess it's a neutron star is what it turns into, but in the process, it turns into a supernova. That process happens very, very quickly, and it happens at precisely this 1.38 times the mass of the Sun. So if you have a white dwarf that is less than 1.38 times the mass of the Sun, but is accreting matter, is collecting matter, often in a binary system. So if this white dwarf is orbiting let's say a red giant star, it can be collecting the material from that red giant star. It gets to the 1.38 threshold, and then it goes bang, and all of these white dwarfs that we see, these type 1 supernovae, go bang at precisely that mass, and therefore their luminosity is precisely the same amount of energy. It's the same brightness. And so they can be used as what's known as a standard candle. If they've got a standard luminosity, then by looking at how bright they appear to be here on Earth, we can figure out how far away they are, given we know how bright they are at their place of origin, where they happen to be. There's very famous equations in astronomy that are used to do this distance calculation. And so the thing is that in 1998, when they looked at the brightness of these particular stars, they found they were too dim. They were much more dim than what they expected. If anything, they expected them to be brighter. They expected them to be brighter because they thought that, well, the expansion of the universe might be slowing down over time. But it wasn't. it was in fact increasing over time. Over the last 7 billion years or so, the expansion of the universe has been accelerating in its rate. And so taking the apparent brightness of these white dwarfs coupled with the redshift of the light coming from these, well, not so much white dwarfs, from the supernova, from the type 1a supernovas, putting these two things together led astronomers to the conclusion, therefore, the universe is accelerating in its expansion. If that's happening, something is overcoming the gravity that should otherwise cause the slowing down of the expansion. And that something that's overcoming it has been given a label: dark energy, which is the name of a problem, not the name of a solution. After all, we don't know where this energy is coming from, what's actually producing the energy. And I should say, astronomers did they did make a literal list of things that could have explained why these supernovae appeared to be more dim than what they were. Things like dust between us and the supernovae, things like supernovae at these vast distances might have slightly different physical properties to the ones that are here. They ruled all of these things out, and they were left with, well, the only possible explanation that we can think of is that space is expanding at an increasing rate. So for now, we have to take that seriously. The universe is expanding at an accelerating rate. There is this dark energy in the universe driving that expansion, but we don't know what the cause of the dark energy is. It, again, is the name of a problem, not the name of a solution. So in my conversation with David, this turned out to be my final question for David. I haven't published all my questions for David, by the way. I'm going to leave the publication of the full conversation, which I know everyone's been waiting for, until the arbitrary episode 100. So episode 100, look forward to that. There will be a lot of additional material there, questions that I haven't published that you'll be able to hear then during episode 100, which should be out in a few weeks. But this final question I actually left to my father, who is one person who never takes on faith anything I say. It doesn't matter what qualifications I might have in the subjects that I'm telling him about. He sometimes doesn't take my answers seriously. So I said to my father, well, if you could ask David Deutsch a question, what would it be? And it was this one. It was about dark energy. And today, October 27th, happens to be his birthday. So happy birthday, Dad. This question's for you. My last question is from my father, and I'll just ask you this before I go. It's about dark energy. And we know the universe is accelerating in its expansion. It's behaving as if there is negative pressure on the outside of the observable universe. Isn't this evidence that the observable universe is actually inside of a much larger region itself of lower density but magnificently greater size, perhaps infinite in size, and perhaps it's actually got zero density, perhaps this void beyond our universe is the thing into which the universe is necessarily expanding, because we've got positive pressure inside of our universe, and outside of our universe, that's negative pressure. Could this be a solution?
So, first of all, dark energy is just the name given to this anomalous expansion, which we haven't explained.
Yes.
So I think the reason that dark energy was chosen as a name is because of dark matter, where all reasonable theories of it so far have postulated that it's a kind of matter, and it's dark because it doesn't interact with photons and so on. With dark energy, we don't have such a thing. We don't know that there is a source of pressure, or that these observations are caused by something pushing on the universe and so on. But with the prevailing theories of what dark energy does, never mind what it is, but what it does, the universe is not expanding into anything. The universe the length scales in the universe are increasing intrinsically, and this is the same as was the case with the prevailing theories before dark energy. That the universe initially had, at any rate, very near to the Big Bang, it was very small. There was a time when it was only the size of an atom. There was a time when it was only the size of a neutron, and so on. And at that time, and now it's much bigger, the difference between then and now is not that it has expanded to fill a void. It has just expanded intrinsically.
Yes.
And some of the present theories say that it is in fact infinitely large, and that it is infinitely large and homogeneous, so that the total amount of matter in it is infinite. I don't think that there are any theories. I mean, one could easily write down a theory in which the universe was inhomogeneous and we are in the only place in it that has matter.
Right,
But
yes.
that wouldn't help in any way with any of the existing theories. And more generally, by the way, theories of inhomogeneity in the universe, as far as I know, I'm not an expert on this, but I think they've only been invoked by people who want to say that there is no dark energy, that it's just a coincidence caused by inhomogeneities.
Mm, mm. Excellent. Okay, I think that absolutely answers the question. So there we have it. What I would add to what David's saying there, just by way of explanatory notes, is that my father could, in a technical sense, be correct, of course, but what David is saying is that, well, if you did have this perfect vacuum of some kind outside of the observable universe, all you'd be saying really is that the universe, being defined as absolutely everything that exists, would be larger than what we thought, but inhomogeneous. In other words, it wouldn't be roughly the same at every single place, which is what the cosmological principle is. The cosmological principle is this fundamental idea in astronomy, in cosmology, which is that at every single place in the universe, it looks roughly the same. So the density of the universe, the number of stars, galaxies, matter, and so on, is roughly the same. There's no reason to think any one place, like where we are, is privileged, or the other side of the universe is privileged and different, or whatever else, which is a very good working assumption. After all, if it wasn't homogeneous, you'd have some explaining to do. Why isn't homogeneous? And indeed, when we look out into the universe, we see homogeneity, roughly speaking. There are some wrinkles in this where we have the distribution of galaxies being on these filaments around these voids, as if there are bubbles of extremely low density where there are very few galaxies at all, and then the galaxies are distributed as if they're on the surface of these bubbles, which is all very interesting and goes back to quantum theory, but I won't get into that right now. The point is here is if you postulate this inhomogeneous universe to try and explain the observations that we have of the accelerating apparent expansion of the universe, you've got even more explaining to do. It's like, how did it end up inhomogeneous in the first place? What we're observing is the expansion of space, not just the rushing of galaxies through space, which is kind of what would happen, unless, of course, you were trying to say that it's the space itself accelerating into this other different space. So it raises more questions than it solves, this particular theory. We don't have any explanation, so at the moment, it's almost like all explanations are welcome. But we can, of course, as always, we can criticize different explanations based upon the best knowledge we have at any particular time. So it was wonderful to have David weigh in on this question, one of the discussions I have with my father sometimes. One day, maybe David can try and convince my father that we do live in a multiverse. But it's good to have someone who is willing to push back against me on many of these ideas, and who is, of course, a layperson. So happy birthday once again to my father, and happy anniversary to my father and my mother for tomorrow, for their 49th wedding anniversary. Next year is, of course, the big one, and we'll have the big celebration. And once again, episode 100 is going to be the complete conversation with David. I'll release that in full as a celebration, essentially, of Topcast's century of episodes. But until the next episode, bye-bye.